Okay, now we are going to analyze how the motion of a charged particle in an electric field. Okay, first thing is when the charged particle is moving parallel to the electric field. So it is just like the case when an object is falling towards earth or is being thrown upwards. Its movement, so it is like free fall. In free fall, the gravitational field, which is vertical, and you can see when you're denoting gravitational field, the arrow is always towards the earth. There's no question of the other way around. So in that case, the gravitational force, the weight is taken into account, and the work done will be mg, the gravitational force, into the change in height, right? So in other words, the loss in potential energy, it will become the half mv squared kinetic energy. That's one thing. We are talking in terms of energy. The other thing that we can do is we can apply the equations of motion, like s is equal to ut plus half at squared, v squared is equal to u squared plus 2as, and so on. We can apply them because the acceleration is constant, that is equal to g. Similarly, if an object is traveling parallel to an electric field as illustrated in this case, so the equal gaps indicate a uniform field. That means the field strength is same everywhere. So when the charge is at the top also, the field strength is E. When the charge is at the bottom also, the field strength is E. And we know that the electric field strength relates to charge and force like this. So F is equal to EQ. So as long as the field strength remains same, the force is going to remain same. But force is famously related to acceleration using ma. So as long as force remains same, acceleration will also remain same. So when an object is moving parallel to when a charge is moving parallel to an electric field, which is uniform, if the field is uniform, we have a situation where there is an object moving under constant acceleration, and we can apply equations of motion, right? So first way of dealing with such cases is to apply equations of motion. Another thing that you can do is you can think about the work done. So we have the field, and that field is uniform. Remember, the field lines should touch the downward the bottom plate. So here is our hero, the negative charge, or the positive charge. Okay, so it is going to experience a force F, right? Is going to experience a force F, the electric force. So first, if we want to find the work done, the work done is equal to the force times the distance moved, right? Now there are two forces here. One is the gravitational force, and the other is the electric force. If the motion is happening vertically downward, then one is the gravitational force and the other is the electric force. So F, the resultant force F, this is not electric force alone, this is the resultant force of both the mg and the electric force, but we can write electric force as E into Q. The charge into the electric field strength. Let me use small q. So the force, the resultant force acting on the object is equal to mg plus eq, right? But there is an issue. The issue is not an issue, but we also have the equation E is equal to V over D. So instead of E, if I substitute V over D, I would have F is equal to mg plus VQ over D. So this is the resultant force acting on the object. So the total work done is equal to the resultant force F times the distance moved. Let's say that the total distance moved by the charge is d when it passes from top plate to bottom plate, would be equal to mg plus vq over d times d, right? So this gives you the total work done as mgd plus when the d comes in, this d and this d cancels off and we'll have vq. So this is the total work done. Okay, now what happened to this work? So the gravitational force is also accelerating the object, the electric force is also accelerating the object. So the total work done, and you can see here, just like you can see here that this is the loss in gravitational potential energy, mgh. When the object comes from top to bottom, it falls through height of d, so the loss in gravitational potential energy is mgh. Okay, so this work done, the work done by both the electric force and the gravitational force becomes the gain in kinetic energy, right? So this work done, mgd plus vq is equal to half mv squared, right? So if we put up the equation, if you try to find the work done by the electric force, that would be equal to the gain in kinetic energy minus loss in potential energy. The gain in kinetic energy minus the loss in potential energy. Okay, so the work done by the electric force, would be equal to gain in kinetic energy minus loss in gravitational loss in GPE, gravitational potential energy. Now, depending on the situation, if the object was going upward, the energy conservation would change accordingly. So you can deal with this situation either using equations of motion or using energy conservation.